What I like to talk about next is methods of finding integrals of powers of the tangent, secant, cotangent, and cosecant. And the methods we used to do that are going to be very similar to the ones we developed in the last lecture for powers of the sine, for integrating the powers of the sine and cosine. Before we do that, we really need to have integrals of just the base functions, the integral of the tangent, integral of the secant, and so on. So we're going to take a quick diversion here and take a look at those integrals. Then we'll jump back in and start looking at how we can integrate powers of these functions. So integral of the tangent function, I think we've actually done this one before at some point, but it bears repeating. I'm just going to rewrite this kind of in the obvious way. I'm going to make this the sine of x over the cosine of x dx. And then I'll do kind of the obvious substitution here. I'm going to let u equal the cosine of x. So du equals negative sine of x dx. You notice I've got a sine of x dx here. All that I'm missing is the negative sign. So negative du equals sine of x dx, and I'll make some substitutions. So this is going to be the integral of the sine of x dx is going to become negative du, and cosine of x is u. So this is the integral of negative integral 1 over u du. And we know what that is, right? This is negative natural log of the absolute value of u plus a constant. And then I'll put the cosine back. So this is negative log absolute value cosine of x plus a constant. That's a perfectly good way to write it. Although sometimes it's convenient to bring that negative exponent in and make this the log of the absolute value of cosine of x to the negative first, which is 1 over the cosine of x. 1 over the cosine of x is the secant of x. So this is also equal to the natural log of the absolute value of the secant of x plus a constant. So next, I wanted the integral of the cotangent of x. And we could do this in a very similar way, right? Make it cosine over sine and do another substitution. But there's another method that I think is a little more straightforward. You can form your own opinion here. So what I'm going to do is I'm going to let x equal pi over 2 minus u. I know that's a little odd. Usually it's u equals, right? But I'm going to let x equal this thing. Then this becomes the integral tangent pi over 2 minus u. And what is dx? Well, dx is negative du. So I'll put negative du in here. And this equals negative ln absolute value cosine pi over 2 minus u plus a constant. Now, here comes the cool part. Tangent of pi over 2 minus u is cotangent. This is negative integral cotangent of u du is equal to negative ln cosine pi over 2 minus u is the sine of pi over 2. Excuse me, is the sine of u. So this is the absolute value sine of u plus a constant. And then multiply through by negative 1. And we get the integral of the cotangent of u du is equal to the positive logarithm of the absolute value of the sine of u minus c plus d plus a constant, right? Some constant over there. And that's what we wanted. I know we originally did it in terms of x and not u, but the variable that we use doesn't matter. Replace the u's with a's if it makes you feel better. We really could go back and put x's in there now. I'm reluctant to actually write it that way because that would be using x to mean really kind of two different things. But that's our formula. The integral of the cotangent of x, and I'm going to write it up here, equals the log, the absolute value of the sine of x, plus some constant. So how about the integral of the secant of x? This is one where you have to just kind of watch it happen and sit back and appreciate the creativity of whoever originally came up with this. Here's what I'm going to do. I'm going to multiply the top and bottom of this by secant x plus tangent of x. Dx. Of course, that's just one, right? I can multiply the top and bottom by the same thing, and it doesn't change anything, right? So now let's multiply this out. This is the integral secant squared x plus secant x tangent of x over secant x plus tangent of x. And I want to pause here, give you a second to think about this. See if you can see where we're going to go next with this. Okay, so what hopefully you noticed is that the numerator of this is the derivative of the denominator. So I'm going to let u equal secant x plus tangent of x. Then du is equal to secant x tangent x plus secant squared x dx, and that's just our numerator. Right, so the whole numerator becomes du. This is the integral of du over u, and we know what that is. That's the log of the absolute value of u plus a constant, and now we can drop u back in there. Log absolute value secant x plus tangent x plus a constant. There's our integral of the secant function. So this is the last one here. I want to find the integral of the cosecant of x, and I'm going to do the same thing that I did with the cotangent. I'm going to let x equal pi over 2 minus u. So dx is negative du. And if I make these substitutions, this is negative integral secant pi over 2 minus u du equals the log absolute value secant pi over 2 minus u plus tangent pi over 2 minus u plus a constant. And now we get all the same nice conversions here. This is equals the integral cosecant u du, which is what the variable doesn't matter, right? This is the integral that I was looking for, equals the log of the absolute value of the cosecant of u plus the cotangent of u plus the constant, and then multiply through by -1, and we get what we wanted. The integral of cosecant u du equals negative log absolute value cosecant u plus cotangent u plus some constant. There's our last one. Okay, so now that we've got integrals for all of the 6 standard trig functions, we can circle back around to the main topic of this section and start thinking about how we can find integrals of powers of these 4 functions.